So let's look at some examples for partial fraction decomposition. And so just kind of some quick background here. If we have an integral like this with a higher degree on top than on bottom, we've got to use long division to rewrite. So after we do longhand division, we get this expression written as x plus 1 over x plus 2. And that we can find the integral of fairly easy. And this 1 over x plus 2 becomes a natural log of x plus 2. Great. Well, if we have an integral that looks something like this, where the degree on top is smaller than the degree on bottom, we can't do longhand division, so we can try use substitution or other things. They're not going to work. So the goal here is to take this expression, factor the bottom. If it doesn't factor, then this is not going to work. And then we can break it up into two fractions called partial fractions. And they have the denominators or the factors there. So if we can do that, then we can take the integral because we can integrate these separately here, and we just get natural logs. So that's the goal, that's the idea. So let's look at a couple examples and see how we can do that. So we're going to use this partial fraction decomposition. We got to watch out when we have factors that have multiple linear factors, meaning we have a linear expression to some degree, bigger than 1. Then we've got to include all of the powers of that linear factor. All right, so here we have an integral we need to work with. So we want to factor the bottom. And so we're going to pull out an x, and that leaves us with x squared plus 2x plus 1 times that x on the bottom, and then the same top. And we want to go a little further here, so we want to integrate, not integrate yet. We want to factor some more, so we ask ourselves, can we factor that? And we can. It's x plus 1 times x plus 1. All right, the top's going to stay the same. And we got x plus 1 times x plus 1 there, so we'd actually like to write that as x plus 1 squared. So let's go ahead and erase that, and we'll change that to x plus 1 squared. Great. Well, now we have it all broken up. So we're going to take that fraction, and we want to break it up into multiple fractions here using our fraction decomposition. We're going to decompose it into, and we're going to shoot for 3 fractions actually, all right? So we have a, I'm actually going to use a capital A we like to use here. So a over x, so the first factor is x. The second factor is x plus 1, and since we have x plus 1 squared, we need to have x plus 1 to the first and x plus 1 squared. All right. So we want that to be equal here. So what we're going to do is we're going to simplify this fraction here. And so we're not doing anything with the derivative yet, or the integral there yet. All right. So our common denominator is x times x plus 1 squared. So we're going to multiply these top and bottom to be able to get a common denominator. We need to multiply the first fraction by x plus 1 squared on the top and bottom. We need to multiply the second fraction by x on top and bottom, and we need another x plus 1 because we're going to need x plus 1 squared. And over here, what do we need? We need an x. We have x plus 1 squared. We need an x. So we're getting a common denominator there. So when we add this all together, let's see what we get. Well, the denominator is going to be x times x plus 1 squared. The numerator is going to be a times x plus 1 squared plus b times x plus 1 plus cx. So that's all these tops put together there. And the bottom is our common denominator. Great. Well, what we see is that we have over here in this expression, notice these are all equal. That's important. These things are all equal. These two fractions look a lot alike. The denominator is the same there. So we want this top to be equal to this top. So let's set that expression equal to each other, and we can solve for a, b, and c. So that gives us 5x squared plus 20x plus 6 equals a times x plus 1 squared plus bx times x plus 1 plus cx. A whole lot of variables there, a whole lot of unknowns. All right, so what we're going to do is we're going to use a clever approach here. We're going to pick an x, and we'll watch a lot of these cancel out so we can solve for a, b, and c. Well, if we pick x to be 0, it's going to wipe out these two terms. And let's see what happens here. So when x equals 0, let's substitute x equals 0. Well, when you put 0 into all of these, 0 times 5 is 0, 0 times 20 is 0, plus the 6, so we get 6 equals, plug in 0 here, we get 1 squared, which is just 1, so that's just 1 times a. Plug in 0 here, and it wipes this term out. Plug in 0, and it wipes that out, and we've got a. Great. Now, we need to get b or c here, so let's try a -1. How about that? Because that'll make the other factor become 0. So when x is -1, let's work it out. We got -1 squared, which is 1 times 5. That's 5. So we get 5. -1 times 20 is -20 plus 6. We'll clean that up in a second. When we plug -1 into here, this becomes 0 and wipes that out. Plug in -1, it wipes that out. And plug in -1 here, we get a -c. So this gives us, well, what do we have? 5 plus 6 is 11, minus 20 is -9. So -9 equals -c. So that means that c is 9. Well, how do we get b now? Well, we know a lot of stuff. We know a, we know c, we don't know b, and we can pick an x value. Pick an easy one, maybe like 1, okay? We already used 0 and -1, so don't use that again. Plug in 1, and we have 5 plus 20 plus 6. And over here we have a, which is 6, times 1 plus 1, which is 2 squared. Okay, so that's 6 times 2 squared, which is 4. Plus, we don't know b, but we're plugging in x equals 1, so that's 1 plus 1 is 2 times 1, which is 2. And we know that c is 9, and x we just said was 1. So cleaning this all up, we get 31. 24 and 9 is 33. Subtract 33 from both sides. -2 equals 2b. And that means divide by 2. b equals -1. All right, we found all the good stuff. We got A, we got B, we got C. So we can now go ahead and write out our fraction. Let's go back to this this form right here in the red part there. And let's come over here. All right, so this is now equal to the integral of 6 over x. Again, we're using this expression here and using the numbers we know. B, we found out, was -1. So we're going to have -1 over x plus 1. So minus 1 over x plus 1. And then C was 9. So we're going to have 9, plug this 9 in for C, 9 over x plus 1 squared. 9 over x plus 1 squared dx. We can now take the integral of each of these parts individually. All right, so this is going to be, when you integrate this, you can pull the 6 out, and you'll have 1 over x, and that is the natural log of x. So pull the 6 out of the integral, natural log of x. And then we've got this minus, and that is the natural log of x plus 1. We're really doing some u substitution there, but the derivative of x plus 1 is 1, so nothing special really needs to happen. And then here, we need to do some u substitution. So this is, if x plus 1 is u, this is u squared. We can pull the 9 out, all right? And so this is u to the -2, and then we're going to add 1. We get -1 over 1, so we're going to end up with 9 over x plus 1 to the -1, which we've dropped down to the 1. All right, and actually it's going to become negative, right? So what's happening there? Here's what we have. Pulling out the 9, we've got u to the -2 du, and we are going to have a negative here. So that'll be u to the -1 divided by -1. That's where this negative's coming from, okay? And the u drops down, which is x plus 1. All right, plus c. And I think that's it. That looks pretty good. So again, we needed a natural log here because these were to the first power. This was to the second power. So any other power in the denominator is not going to be a natural log. It's going to end up being another fraction. All right, so one last situation here, and that's when we have some quadratic factors here. So whenever we have a quadratic factor in the denominator, then we're going to need a term that looks like this. You'll have your quadratic factor, and instead of just putting a single number up here, we'll need bx plus c, because the degree here needs to be 1 less than the degree on the bottom. So what does that mean for us? Well, it means we're going to take this integral here. That's already factored on the bottom. That's kind of nice. And let's break it into 2. We have a over x times, nope, just x, sorry, plus bx plus c all over x squared plus 4. All right, so we need this to be linear, first degree for a second degree denominator. All right, and we're going to find out what makes this x minus 8 equal to this. Well, first before we do that, we've got to make one fraction here. So let's make one fraction out of this. So we're going to multiply top and the bottom here by x squared plus 4. And on top and bottom. Okay, so we're getting a common denominator. This one we'll need to multiply by x on top and bottom. All right, and so let's see, that'll give us something like this, where we have our common denominator of x times x squared plus 4, and a numerator of a times x squared plus 4 and bx plus c times x. All right, so now we have two equations that look the same. We've got this equation here that we started with, and this equation, they look in the same form. Notice they both have the denominator here. So we need to find out what a, b, and c have to be to make the top equal to x minus 8. So we have x minus 8, then we've got a times x squared plus 4, and bx plus c times x there. And we're going to use the same technique where we're going to let x be a certain number. And we'll notice that this will never be 0. X squared plus 4 will never be 0. You can't, because it's always positive. So we're not going to cancel this out. But what number will cancel this whole term out? Well, that is 0, right? So we choose a number that will cancel one of the terms out. And we have 0 minus 8, which is negative 8. And then we have equals a times 0 squared plus 4 is just going to be 4. Actually put that over here, times 4. And then, well, here this is going to be b times 0 plus c times 0. Since this is 0, the whole thing will be 0. So that whole thing is zeroed out. Okay? So about there, we'll divide both sides by 4. Divide by 4, and we get a is equal to negative 2. All right. So that's great. So we have x minus 8 equals negative 2 times x squared plus 4 plus bx plus c times x. All right. And well, we got a challenge here with b and x. So what we're going to have to do is we're going to end up with a system of equations here. So pick some nice numbers. Let x equal 1 maybe is a nice number. And that'll give us negative 7. And this will be 5 times negative 2, which is negative 10, plus b times 1 plus c times 1. And that 1 out there won't matter, but I'll leave it there for now. Let's add 10 to both sides, and we end up with 3 equals b plus c. And then we want to pick another one here. Let's try another x value. So another x may be negative 1. And that's going to give us, plugging it back into here, x is negative 1, plug it in, we get negative 9. And this is going to be still 5 times negative 2, that's negative 10 again. And this is going to be negative b plus c times negative 1. And let's add 10 to both sides. That gives us 1. And distribute here. It gives us b minus c. Okay. So now we have these two equations. Let's copy this one down here. And we got a system of equations. And that's turned out pretty nice. So let's add the equations. And so if we add the equations, 4 equals 2b, and the c's cancel, so b is 2. And we can substitute that back in there. And that gives us 3 equals 2 plus c. So c is 1. We've got our ABC. And our a, where was our a? There it is. So now all we got to do is plug that back in, and we can take our integral. So we're going to plug it back into this red integral up here. A is negative 2, b is 2, and c is 1. All right, keeping that in mind. All right, we have the integral of a, which is 2 negative all over x plus bx plus c, that's 2x plus 1 all over x squared plus 4, and dx, that whole thing. All right, and we can do that, I think. Let's find out. Actually, before we do anything with this, we need to break this up because of the plus here. You'll notice here, if you take the derivative of this, you'll get 2x, so you could do some u substitution here. But that 1's causing a problem. So what we need to do with this is we need to break this into two fractions, 2x over x squared plus 4 plus 1 over x squared plus 4. All right, so that fraction, because it's plus, can just be broken up like this. Okay, and so let's find the derivative. We got that equals -2 natural log of x plus, I'm going to use some u substitution here. U is x squared plus 4, and du is 2x. Notice we have that. So we can go ahead and take the derivative of this. The derivative will be, because when we do our u substitution, it'll just be the natural log of x squared plus 4. Okay, and you can double check. Take the derivative of this, chain rule. Derivative of the inside is 2x. Derivative of the whole is 1 over x squared plus 4. All right, it's all there. So now this is not u substitution, but recognize this form here. You recognize this. This is like a u squared plus an a squared, and that is our arctangent. Remember that? Okay, derivative of arctangent is 1 over u squared plus a squared. So this is u is x and a is 2. And so this is 1 over a, 1 over 2, times the arctan of x over 2. All right, there it is. So a little more complex there when we have the a quadratic denominator there. And we're mostly focused on AP. The AP test, when it comes, will be only focused on the linear terms, but it's good to see this quadratic as we are working with it. So, all right, hope that helps. And go ahead and break those fractions up. Then put them back together, solve for those A, B's, and C's, and use your natural logs. Keep working at it, you'll get it. Good job.